In today's lecture, we're going to explore one of the most powerful concepts in PLC ladder logic programming, branching. Branching allows us to create parallel paths in our logic, giving more flexibility to design control systems that can respond to multiple input conditions or control multiple outputs simultaneously. From there, we'll look at limitations, how some PLCs restrict the number of contacts or branches you can include in a single rung, and why vertical or backward logic paths are not allowed in ladder logic. Finally, we'll review two key input instructions. Examine if closed, used for testing when an input is on. Examine if open, used for testing when an input is off. Let's begin with the most basic form of branching, creating parallel input paths. In this example, we have two input instructions, A and B, connected in parallel. This means the rung will be true if either A or B is true. In other words, only one of the two inputs needs to be active to complete the circuit and energize the output, labeled C. This type of logic is similar to an OR condition in Boolean algebra. The output turns on when any one of the parallel paths provides continuity. Parallel branches like this are extremely useful when you have multiple start buttons, sensors, or permissive signals that can each trigger the same output. Now let's take branching a step further by combining series and parallel conditions to create multiple logic paths that can turn on the output. Input A is in series with B, and a parallel branch contains C, giving two ways to energize D. The top path is true when A is on and B is off, while the lower path is true when C is on. This allows the output to activate under different conditions, such as automatic operation through one set of inputs or manual control through another, making ladder logic versatile for real-world systems. Now that we've seen how branching can combine multiple inputs to control one output, let's look at the opposite case, where a single logical path controls multiple outputs. This is called output branching. Here, inputs A or B provide a true logic path that energizes all three output instructions C, D, and E. Essentially, one condition or combination of conditions can activate several devices at once. This is very useful in automation when one event should trigger multiple actions. For example, pressing a start button might turn on a motor, energize a solenoid, and illuminate an indicator light simultaneously. This slide shows an important detail about nested branches and a limitation you might encounter when programming them in certain PLC models. In the top example, we see a branch that contains another branch inside it. This is what we call a nested branch. The rung logic includes instructions A, B, and C in series, with an additional path that contains D nested inside the main branch, and it providing an alternate route. The issue here is that some PLCs or programming software will not allow this type of structure to be drawn directly, because it becomes difficult for the processor to interpret the exact logical order of evaluation. However, the same logic can still be achieved by reprogramming it in a logically equivalent form, as shown in the lower example. Instead of creating a branch within a branch, we can repeat one of the instructions, in this case C, to flatten the structure. This produces the same logical result while conforming to the software's programming rules. This approach is a common programming technique in ladder logic. When a certain graphical structure isn't allowed, we can rewrite it in an equivalent way that preserves the same truth table and logical behavior. In ladder logic, PLCs require all rungs to flow horizontally from left to right, as the processor reads each instruction in that direction to determine logic continuity. Vertical contacts, like C in the top diagram, are not allowed because they create ambiguity in the logic path, causing the PLC to flag an error. The lower diagram shows the corrected version, where the same logic is rewritten into parallel branches that follow proper programming rules. For practice, let's take a look at the Boolean expression for the lower diagram. Each group of letters represents a valid path that can energize the output Y. For instance, AD means both A and D must be true. BCD requires B, C, and D to all be true. B means B and E must be true. And finally, in the last rung, AC means AC, and E must all be true simultaneously. If any one of these four combinations is true, the output Y will energize. So the final Boolean expression is written as Y equals AD plus BCD plus BE plus ACE. In summary, this method preserves the same logical behavior while eliminating vertical connections, ensuring that the PLC executes the program correctly and efficiently. This slide illustrates a key concept in how the PLC executes your program: logic flow direction. A PLC always scans each rung of ladder logic from left to right. It checks each instruction in sequence to determine if a complete path of true conditions exists from the left power rail to the right. Only when that continuity is maintained does the output instruction, usually a coil, become energized. In the example at the top, the circuit contains several branches, but one of them forms a path that appears to flow from right to left. The processor, however, will never evaluate logic in that direction. As a result, the contact combination FD, B, C would be ignored, even though it might look electrically valid on paper. The Boolean equation shown, Y equals ABC plus AD plus FE plus FDBC, includes all intended paths, but because the PLC cannot process backward logic flow, the last term, FDBC, would never be executed. The corrected version shown at the bottom rearranges the contacts so that all logic flows properly from left to right. Each valid path is now represented by its own rung, ensuring the PLC reads and executes every combination as intended. This example reinforces a crucial habit in PLC programming. Always design your logic to flow consistently left to right, never vertically or backward, so that the controller can interpret and execute your instructions correctly. Now let's take a moment to review two of the most frequently used PLC input instructions: the examine if closed and the examine if open instructions. The XIC instruction checks whether an input bit is true, meaning the contact is closed or the device is energized. When the condition is true, the XIC allows logical continuity, enabling the rung to be true and the output coil to energize. On the left side, you can see a hardwired circuit that includes two push buttons, PB1 and PB2, connected in series to control a pilot light. On the right, the PLC version replicates the same behavior using two XIC instructions, PB_1 and PB_2, in series. It's important to note that the PLC doesn't care whether the physical device in the field is normally open or normally closed. What matters to the controller is whether the input bit in the data table is true or false at that instant. So, in short, when the contacts are closed, that is, when the signal is true, the XIC instruction allows current to flow in the logic diagram, just as it would in a physical circuit. The XIO instruction checks whether an input bit is false, meaning the contact is open or the device is not energized. When the input bit is 0, the XIO allows logical continuity and the rung is true. When the input becomes 1, or energized, the XIO opens and breaks the logic path. Looking at the diagram, on the left we have a hardwired circuit with a normally closed push button controlling a relay coil, CR, and a pilot light, PL. When the push button is open, not pressed, the relay coil is de-energized and its normally closed contact allows the pilot light to turn on. On the right, the PLC equivalent uses an XIO instruction to represent that same behavior. The rung is true, and the pilot light output turns on when the external push button is open. Pressing the button closes the contact, causing the rung to become false and the output to turn off. In summary, the XIO is used anytime you want a rung to be true when a condition is not present. For example, when a stop button is released or a fault signal is inactive. This slide shows how the PLC evaluates the XIC, XIO, and OTE instructions step by step. At the top, you can see how each instruction responds to the bit value stored in the controller's data table. If the bit is 0, the XIC instruction is false, the XIO instruction is true, and the OTE instruction is off. If the bit is 1, the XIC instruction becomes true, the XIO becomes false, and the OTE stays off unless both input conditions are true at the same time. In the ladder rung shown in the middle, the XIC and XIO instructions are connected in series, controlling the output coil OE. This means both instructions must be true for the output to energize. The table at the bottom shows how the logic changes over time. At time 1, all instructions are false and the output is off. At time 2, both XIC and XIO are true, so the output turns on. At time 3, XIO becomes false, breaking the path, so the output turns off. At time 4, both inputs are false and the output remains off. This example demonstrates how the PLC continuously checks input bits, evaluates the rung from left to right, and updates the output based on whether the conditions of the XIC and XIO instructions are true or false. In the next chapter, we'll explore how physical wiring diagrams relate directly to PLC ladder programs. You'll learn how to interpret and create wiring schematics for relays, contactors, motor starters, switches, and sensors, and then see how those same systems are represented in software through ladder logic.